Okay, I wanted to say something more about complex functions. And I don't know if I can really give you a very full idea of how extremely useful they are. Dr. Diesel was going to teach complex analysis at some point, and I do recommend you take that class because complex functions are very beautiful, extremely useful. All right, so the point I'm going to make in this short video is that complex functions give a compact representation of certain types of functions from R2 to R2. Now, in the other video I made, I said that dynamical systems, you do sometimes think of maps from R2 to R2, mappings from the plane to the plane. Now, complex functions give a very nice way of representing certain types of functions like this. For example, consider the function f of z equals z. That's the identity function. You could also represent that as f of xy is equal to xy. Now, consider taking a walk around the origin. Okay, I mean, here's my axis. If I walk around the origin, and then I consider f of that walk, so I take f of all of those points. Well, f is the identity, so if I walk around the origin, then the image under f is also going to go once around the origin. So we get this result that if I move once around the origin, then I map under f, I also move once around the origin, and that's 2 pi radians. Suppose you have the function f of z equals z squared, and you go once around the origin, and you take f of that walk around the origin. Well, it turns out that under the f, you'll end up going twice around the origin. Okay? Suppose I take f of z equals z inverse. Now, if I walk once around the origin, and I take f of that walk around the origin, it turns out I will go, it's not 2 times, sorry, that's incorrect. It's once around the origin in the opposite direction. So I'll be going in the opposite direction. Okay, so let me explain this picture here in terms of these observations. Okay. This is a complex function. The expression for the complex function, don't remember exactly what it was. Let me look it up. I'll pause this for a second. All right, I've written the function over here. F of x equals x squared minus 1 times x minus negative 2 minus I squared divided by x minus negative 2 minus x squared minus negative 2 minus 2i. Right. So notice something about this. What are the roots of f? Well, they're roots at +1 and -1. Okay. That actually corresponds to these 2 different points here. This one here and this one here. +1 and -1. Right. Now what's actually going on here? Notice how you have a color wheel here going from, let's start at red. Red goes to purple, goes to blue. If we're running counterclockwise, red goes to purple, goes to blue. Okay, and you're running through all the colors exactly once. Okay, here we have another same situation here. If you're looking at the colors, red goes to purple, goes to blue, goes counterclockwise, and it runs through all the colors once. Now, why is that? Because near this point, the function looks approximately like x plus 1. In fact, it looks like sort of like the identity function. So we're getting once around the point gives me once around, the image also gives me once around, just like in this original example. Same here. If I have a root here, then I'm simply going around 0 once. It's a simple root. Okay. Now, at this point, when x is equal to 2 plus I, x is equal to negative 2 minus I, it's a double root. Since I'm going to have a double root, I'm going to be going around the origin twice. So look at the point, that's the point here. If I look at the color wheel, I start at red, I go counterclockwise, same, I go around, and then I hit red again. So that indicates that I'm going around the 2 pi twice. I've done a total of 4 pi around this point here. Now let's look at the other 2 points. There are 2 more points here and here. It turns out that these are the roots of the denominator. Okay? If I have a root of the denominator, then I'm going to have a place where the denominator is 0, it's going to blow up. That's like 1 over z. Okay? So that should indicate that I go around the colors counterclockwise 1 time. And you can see that's what happens. If I'm considering going from red goes to purple goes to blue, here I'm going clockwise instead of counterclockwise. When I went around this one here, which was the corresponded to x equals 1, when I go red to purple to blue, I'm going counterclockwise. At this point, if I go red, purple to blue, I'm going clockwise. Opposite direction, that corresponds to a root in the denominator. Same thing here also. If I go red to purple to blue, and I go around, I'm going clockwise. That indicates that this is what you call a pole. It's the opposite of a root. It's where the function blows up. You can see these contour lines. The contour lines are increasing magnitude. So you can see, for instance, at this point, the magnitude is 0. That's in the center of this contour line. This also has a very small magnitude. Here, here, and here have small magnitudes. These have large magnitudes. You can see that they're out in kind of in the outer part where these unbounded lines are. So that kind of gives you an idea how the configuration of this complex function relates to the arrangement of the roots in the numerator and the denominator. Okay? And this information turns out to be very useful when you're looking at characteristics of maps. All right, that's all I have today.